Okay, we're given 4 polynomials. Negative 4 minus 3x, 8x squared plus 2, 4x squared plus 2x, and x cubed. And we're asked to determine whether they're linearly independent. Well, we start with the definition of linear independence. This is automatic. And if we don't know what that definition is, we're kind of lost from the beginning, so we just have to have that definition down. Definition says that the vectors v1 through vn are linearly independent if a sum of their multiples, c1 v1, c1 2, c2 v2 plus and so forth up to cn vn, if that sum is 0 if and only if all the c1, c2 up through cn numbers that you're multiplying them by are 0. So we write that condition down. First of all, we write this equation out with the vectors. Okay, c1 times this vector plus c2 times this one, c3 times this one, c4 times this one is 0. Now, people used to think of the vectors as things you can draw in R2. Okay, but we, a long time ago, generalized vectors, showing that P2, P3, and so forth are vector spaces, showing that M22, M5, 4 matrix, sets of matrices of given dimension constitute a vector space on addition by addition and multiplication by real numbers. We need to understand that these functions are being regarded as vectors. Okay, so it looks a little weird. You know, it looked a little weird to me when I first learned this. Oh, those don't look like vectors. That's not what I think of as a vector. Well, you got to generalize what you think of as a vector. Okay, so these are treated as vectors. They are vectors in a vector space, P3. Okay, well, anyhow, we see if this sum is equal to 0. Now, being equal to the 0 vector means being equal to 0 for every value of x, every possible value of x. Okay, well, we collect terms in this. You know, we do all the multiples of x4, all the multiples of x4, x cubed, all the multiples of x squared, all the multiples of x, and all the numbers that are there bare without any multiples. So we just rearrange this into this form. And we see that, well, the only way this is going to be 0 for all values of x is for this to be 0, and for this to be 0, and for this to be 0, and for this to be 0. Okay, so I say, and it's a little blurred, it says, it's so if and only if, then, well, I set this equal to 0, set this equal to 0, I set this equal to 0, I set this equal to 0. That gives us, then, a matrix equation. Here we got it. Okay? Now, so, it's linearly independent, meaning this, and this is so if and only if this system is so, which is true if and only if this matrix equation is satisfied, which is true if and only if the determinant of this matrix is 0, or alternatively, the matrix reduces to the identity, and so forth, or the augmented matrix reduces to the identity with a bunch of zeros over here. You could use any of those criteria to establish whether this is so. In this case, it turns out to be so, and you can verify that for yourself. But since it's so, whatever way you solve this thing, you find, most easily, if the determinant's not 0, I can invert this matrix. The inverse matrix times the 0 vector is going to give me 0, so the C1 through C4 will equal the 0 vector. So that all the C1 through C4 are 0. So we've concluded that this is linearly independent. Now there's actually an if and only if. And what we've just proven is that this is true only if these are linearly independent. To prove that they're true, that this is true if C1 through C2, C1 through Cn are all 0, well, that's really simple. If all these are zero, then this is zero and this is zero, and we just get a bunch of zeros and we add them up and we get zero.